So, good afternoon, everyone. Welcome to this third interaction session for NPTEL course Experimental Physics Second, which is being taught by Professor Amal Kumar Das from IIT Kharagpur, and I am teaching assistant for this course. I am Renalini, PMRF Research Scholar from School of Physics, University of Hyderabad. So, last interactive session, which was the second week, we had discussed significant figures and how to do maths for significant figures. That is, when the numbers or the measurements are to be added or to be subtracted, or their product or division is to be handled, then what rules we have to keep in mind. Based on that, we had done a lot of questions which included rounding of the numbers to certain digits also. Also, last time we had done a lot of questions based on error analysis, right, which was basically discussed in week 1, and last time we did a lot of numerical problems based on that. Also, we later end we started discussing, because since this second module will be covering mostly optics based experiments and some of quantum mechanics based experiments as well. So last time we started by talking about the basic optics tools that we find in an optical lab. So in this week's, as you must have seen in the lectures, so sir has started okay, so he started first with explaining these components, how the different type of mirrors are there, different type of lenses are there, and what is reflection laws and refraction laws. We'll discuss them, and also we'll be discussing few experiments that were there in this week, and of course we will do numerical problems based on those topics. So okay, let's start again. So as I said, the most of the experiments in this module is based on optics experiments. Thus we should have some idea, not some idea, we should thoroughly know these components that we used in an optical lab. So we'll be starting to discuss the mirrors, various mirrors and types of lenses that we used in a optical lab. So mirrors can be of three different types. There are more actually possible. Okay, so basically that we talk about are plane mirror, concave mirror and convex mirror. So plane mirror, we all know that we mostly see around us at our homes as well. It's basically a flat surface which has been polished on one side by some silver based chemical, because of which the other side becomes highly reflective. Right. I mean, all the material actually reflects light, but it depends on the surface. Like if there is some not so flat surface, it will scatter the light in random direction, and thus we don't get good reflection from it, and thus we are not able to see any image. But with a mirror, what happens, whatever light goes, it completely bounces back and we are able to get the image. So this is for flat mirrors. Similar to flat mirrors, we have spherical mirrors. Okay, let's talk about that later. Now let's start. What are the principles on which these mirrors work? So they include reflection of the incident light, and these reflections of these incident light follow certain laws which are called laws of reflection, which are valid for both plane mirror, this is our flat or plane mirror, and curved mirrors, or curved mirrors you can call it, or they are also called spherical mirrors, because they are a small part of, we can say, a whole sphere, right? Like you must already be knowing. So if we take a spherical glass and cut a very small part of it, then that part we polish from one side, it could be inside or outside, then the opposite side becomes reflecting. So that's why this is also called spherical mirrors, or because we are taking small part of it, so it's not flat, it's curved, so we also call them curved mirrors. So these laws of reflection, we have two laws of reflection which are valid for both these planes and curved mirrors. So what are these laws? The first law is, it tells that upon reflection from a smooth surface, the angle of reflected ray is equal to the angle of incident ray with respect to the normal to the surface, that is a line perpendicular to the surface at the point of contact. So what it's saying is that, consider this is that smooth surface that we are talking about. This is that smooth surface, polished from one side, so other side is very good in reflecting. Now if then first let's consider an imaginary line which is perpendicular to this smooth surface or flat surface. This is imaginary line which is we always consider perpendicular to this flat surface. Then our incident ray, the angle of reflected ray is equal to this angle of incident ray. Here this is our incident ray, as you can see, and it will be incident on this mirror and will reflect with the same angle. But here angle we are talking about is the angle that this incident ray is making with this imaginary normal which we had considered perpendicular to the reflecting surface. So as you can see in this diagram, this theta1 is the angle of incidence and this theta2 is the angle of reflection. So basically what this law is saying, that we have a reflecting surface and the incident ray which is incident on this reflects with the same angle, and the angle we are measuring from this normal. So what it says is theta 1 is equal to theta 2 from the figure, or if we call this theta I, that incident angle, then we can also say incident angle is equal to reflected reflected light's angle. Another part of this law is that the reflected ray is always in the plane defined by incident ray and normal to the surface at the point of contact of the incident ray. What this second part means is that when we have the same reflecting plane, then this law that we are considering, here the incident ray, reflected ray and this imaginary normal, all these three things are in the same plane. So I mean it cannot form a cone that it's incident. I think in the lecture also you would have seen, I cannot show here like explain in 3D, but what it means is all is in a same plane. All this is a same plane. It's not like this will be in plane and reflected light, although it can be same angle, but it can be out of plane also. But this rule tells us that it has to be of the same angle, also it has to be in the same plane. So this normal incident light, reflected light, and this mirror reflection, sorry, this not plane, but all these things have to be in the same plane. So these are the laws of reflection that all the reflecting surface follows. Okay. Let's do this question first, then I'll explain how the reflection looks like for a curved surface. Here we are seeing the example. Here we are seeing example for this plane mirror with how the reflection law looks for a curved surface. We'll see. First, let's do a small question based on the law of reflection. So the question is, a light ray strikes a reflective plane surface at an angle of 54 degree with the surface. So let's make a diagram as per the question. We have a reflective surface. One side will be polished so that other becomes very good reflecting surface. A light strikes this surface at an angle of 54 degree, but this angle it's telling from the surface. So this incident light is making 54 degree from the surface. Surface means this reflective surface we are talking about. So from the surface, incident light is making 54 degree angle. Okay. This is the information given to us. Now, next part of the first part of the question is calculate the angle of incidence. So from what we understood just a few minutes ago, that whenever we have a reflecting surface, first we have to consider imaginary perpendicular to it, and the point of contact of this imaginary perpendicular line, angle of incidence and angle of reflection, they share a common point of contact and they are in same plane. Now angle of incidence we consider from this imaginary normal to the incident angle. Here we have been given that the angle information they are giving based on the angle between the surface, this reflective surface, and incidence ray. But angle of incidence we consider is the angle between this normal and the incident ray. So this is our incidence angle. Now since I am saying this is imaginary normal, this is imaginary of course, but this is normal. Normal means this is perpendicular to the reflecting surface. That means this angle it's making is 90 degree. Right, this angle it's making is 90 degree. This angle is 90 degree and this 54 degree, which is the angle between surface and incident light. This is 54 degree. Remaining angle is our angle of incidence, and this total you can see is equal to this 90 degree, which is the angle between this imaginary perpendicular and the reflective surface. So from this information we can pretty quickly find out our angle of incidence, which will be 90 degree minus 54 degrees. That will be 46. I think this is okay. Let me just check. 90 minus 54, 36. What? Oh, sorry. Yeah. It's not 100, it's 90 degree. It will be 36 degree. So this is our angle of incidence. Now next question is calculate the angle of reflection. So there is nothing to calculate since we know the law of reflection, which says that angle of incidence is equal to angle of reflection. Thus angle of reflection here should also be the same as angle of incidence, which is 36 degree. Third part of the question is calculate the angle made by the reflected ray and the surface. So as per law of reflection, our angle of incidence is 36 degree, angle of reflection also will be 36 degree. This is reflected ray. Reflected ray or reflected light. Now the question is asking us to find out the angle made by this reflected ray and the surface. That means this angle is being asked. So there are two ways to tell. Again, this imaginary line which is perpendicular to the surface, we can use the same rule. It is 90 degree and one part of this angle is 36 degree. The remaining we need to find out. Let's call it theta. Then this theta will be 90 degree minus 36 degree, which will be equal to 54 degree. Or we can simply see that this theta I is equal to theta r. So remaining 90 minus theta I and 90 minus this unknown should be same, right? So this will be, from the picture we can see and say that it's 54 degree. So angle made by reflected ray and the surface is 54 degree. Angle made by incident light and the surface is also same. So this also we can notice that this angle made by incident light and surface and reflected light and surface is also same, that we have calculated, it's also same. But we have to keep in mind that this is not called incident angle or reflected angle, because that is always measured from the normal to the surface. So although these two also are same, but they are not angle of incidence or angle of reflection. Fourth part of the question is calculate the angle made by incident and reflected rays. So now we need to find out the angle between the incident ray and the reflected ray. So the angle between incident ray and reflected ray is this total, and this total is made up of this theta I and theta r, right? Theta I plus theta r is the required angle between incident and reflected. Theta I is 36 degree, theta r is 36 degree as well, so total will be 72 degrees. So this is our answer. So this is how law of reflection can tell us definitely uh, what is the angle of reflection when the angle of incidence is known. Now, okay, let's understand how the, before this, okay, first I can tell you this also, or I need one slide. Yeah, so we had seen this, this diagram we had seen where we were talking about a plane mirror or plane reflecting surface. Now we'll see how the reflection, angle of incidence rays look like for a curved reflecting surface. So if we have a curved reflecting surface, say this is again how we got this, this is a very small part of a spherical glass, and after cutting it, let me show you again. Here also in this you can see this is how it will look. If you will complete this, it will be a part of a big spherical object. So again to show you, so it will be a sphere and we take very small part, so maybe you cannot even see from your naked eye that it's curved because it's very small curve, but it's part of this, and that's why these mirrors are called curved mirrors, or actually spherical lenses we use more, but curved mirrors at least we call them. Okay, so one part of it, one side of it is polished to make another side highly reflecting. Now for this, because I told you it's part of a sphere, so sphere has this, so we know like there will be a center to this sphere. Okay, like in a circle we have center of circle, the same way for sphere we'll have a center. Why is this happening? Okay, that we call center of curvature. This, for this curvature, that is the center. And if we drop a normal to any part, because it's from the center, any part on the sphere will be its radius, right? So this is also called radius of curvature. This is the center of this curvature, and this length, distance of this center of curvature to any point on this curve is called radius of curvature. We denote it by R, capital R. Anyway, so when we do this to any part of this curve, it's perpendicular. And how to see that perpendicular? If we draw any tangent at that point where this radius of curvature is touching it, from there, why we need this normal? Because we have to define our incidence angle and reflecting, this will be here, angle of incidence and angle of reflection we need to define. For that we need this. So wherever this radius of curvature touches, we make a tangent and then we define, so angle of incidence at this point, and it will again angle of reflection. The law is same, angle of incidence, angle of reflection will be same, and this angle of incidence, this normal, incident ray and reflected ray all will lie in the same plane, that also they follow. And if the light is coming at this angle, then it will make the same angle and go in this direction. But if the incident light is coming through the center of curvature, then the center of I told you this radius of curvature is perpendicular to the surface everywhere. Wherever it touches, it is perpendicular to the surface, right? So this is also the normal. So if the incident light is coming along this, then our incident angle is 0, right? Whenever we have this normal, if the incident angle is coming like this, we say it is making some angle with the normal. But if it is coming along the normal, then the incidence angle is 0 degree. And when the incidence angle is 0 degree, that means reflected angle also will be 0 degree, because the law of reflection will be followed always. So if the incident light is coming along this direction, it will go back also in the same direction. So if it is coming along this, it will go back also along the same line. So this is how the law of reflection looks like for curved surface. This is a concave mirror. Actually, concave mirror, as I said, we have basically two kind of curved mirrors, concave and convex. So both are part of this spherical mirror, but for one case, for concave mirror, we call it concave mirror. We'll see in detail their properties, but how we make them basically is we take the small part of this glass, and when this is the inside part, right? And when I polish this outside part of this glass so that the inside or this curved part becomes reflecting, we'll see again how it reflects the lights. But if inside part is the reflecting and outside part is the polished one, then this type of mirror is called concave mirror. Whereas if again taking the same piece of this glass, and this time I'm polishing the inside part so that outside part becomes reflecting, then this type of mirror is called convex mirror. Okay, so these are the two type of curved mirrors. Now, so here you can see this is what this diagram I have taken from the lectures. So this you can see, it's just they are trying to show that it's part of a sphere, and this P is called pole of the mirror. This focus and radius of curvature, I think I can tell, but I think we should have first discussed. Okay, then in that case I'll explain this mirror then, because it includes all the reflections. So let's finish mirrors first. So as I said, here you can see it's written spherical mirror. I told you in the first slide, we can call them curved mirrors or spherical mirrors, because they come from a sphere basically. So this I told, there is in this diagram, right, that this C, which is the center of the sphere, it is called the center of curvature, and the line from center of curvature to any point on the mirror is called radius of curvature. The same diagram has been, like, now the mirror we have considered vertically. So if you draw a line passing through the center of curvature and passing through the mirror, again it's imaginary line that we are considering, that where it crosses the mirror, that is called pole of the, we call it pole of the mirror, okay, and we denote it usually by capital P. Half of this radius of curvature, this CP here is the radius of curvature, okay. This CP or PC is the radius of curvature denoted by capital R, because it's like radius of the sphere. Half of it is called focal length or focus, and the distance is called focal length. This has a great significance, because if I tell here quickly that whatever light comes parallel to this spherical mirror, whatever incident light comes parallel to it, means, sorry, this imaginary line that I am considering through center of curvature and passing through any point on this mirror. So any line coming parallel to this will be considered parallel, and it will, after reflection, it will always pass through this half of radius of curvature, which point is called focus. So this is also one way to find out where is the focus of this mirror, because we'll make a incident line, make it incident on this mirror, and it will always pass through the focus. And if another thing is, if we make a light incident through the focus of this mirror, this point, then it will always reflect and go back parallel to this line. This line is called principal axis. This line, which is passing through center of curvature and to the pole, that line is called principal axis of the mirror, and any light parallel to this principal axis after reflecting goes through the focus. Another case, any incident light passing through the focus always reflects back and goes parallel to the principal axis. So this, as I said, you can see here that this dashing or this I can see this ridges that I have made or has been made, it shows that this part has been polished. That means the other side is the reflecting one. So as I said, if the outside is polished, inside is reflecting, then it's called concave mirror. And here on the right you can see, here the inside part of this sphere is the small part of sphere is polished, and outside one will be reflecting. So this is the case of convex mirror. But the concept of principal axis, pole, focus, radius of curvature, everything is same. Here also, if light is coming parallel, it will be reflecting. I'll tell you why we have shown it dashed, because it always forms virtual image and we say that it appears to be reflecting to the focus, but we don't see what is on the other side, right? So we'll talk about this, but to understand, these are the basic parts of the curved mirrors or the spherical mirrors, which is center of curvature, radius of curvature, pole of the mirror, focal length, which is half of the radius of curvature. Okay, so next is that how to distinguish. This is again the same, that we have two types of mirrors. One is concave which focuses parallel. This I have already explained, that if outside part of this is polished, then it is called concave. If inside part is polished, then it is called convex mirror. Convex mirror. So this is concave mirror. All the incident lights which are going parallel to this principal axis are, after reflection, are passing through the focus, and all the incident lights which will be incident through this focus will, when they'll go back, they will be parallel. So this is the characteristics of both of these. But okay, focus parallel beams of light to a point. Convex, it seems whatever parallel incident lights are going, they are spread out. They are spread out. When you will see from this side, you will see that parallel rays were incident on the convex mirror. This is convex mirror, and they seem to be spreading out. But focus of this curved mirror, which is on the another side, it appears that these reflected lights are coming from that focus. So the rule is same for it, but here we can see it being focused, and here we see it going spreading out, because, and it just appears to be coming from this focus which is on the other side of this mirror. So now the characteristics of concave and convex mirror makes them easy to distinguish. Like one thing should be known, that there are two type of images formed in mirrors. Okay, one is real image, another is virtual image. Real image is always inverted, and we can see it on a screen, whereas virtual image we cannot obtain it on a screen, but it is always erect. What do we mean by this is, like what image we see in plane mirror also, if we have some object, say, I don't know, a tree for example, a small plant or a tree in front of a plane mirror, what we see in the mirror is not a real image, and we cannot get it on a screen. We just can only see it in the mirror, and it's always the whatever image you will see in the mirror, that will also be like this, right? It will be, of course, left and right of the image, any image gets inverted, but up and down is same. If the object is like this, then image will also be like this. So this is called erect image. If for any type of mirror, object is like this, but some type of mirror it is, under which we don't know, just say right now we may not know, but if the image is coming out, sorry, I should have drawn, image is coming out like this, then it is a real image, and it's always inverted, and we can also obtain it on a screen. So this is the property of these two type of images that are possible. Now convex mirror always forms virtual image and erect image, whereas concave mirrors, the image that we obtain from concave mirror, it can be either erect or inverted, that is either real or virtual, depending on the distance at which the object is kept from the mirror. So for convex mirror, which you know we always use in our vehicles, because of course there we don't want to deal with inverted images of vehicles coming towards us, so we use convex mirror in vehicles, because it always forms erect image, so there is no problem, which is a virtual image. But for concave mirror, the problem is, depending on the distance the image can be erect or inverted. That's why we never want to use concave mirror as our vehicle side mirrors. So let's see at what distance how the image changes for a concave mirror case. So one case is when the object is kept between the center of curvature and the focus. So we told there is one focus point on this imaginary principal axis. This is the principal axis. If I extend it further, this is focus point, double of it is radius of curvature, double of it is center of curvature or radius of curvature. So if my object is kept between this focus point and center of curvature, then I'll obtain the image as inverted and real. So this also we'll see when we'll understand the experiment that was done, where we wanted to find out the focal length of the concave mirror. So how it happens is, the farthest it is, the object, the closer the image gets. So like, okay, maybe we'll discuss this when we'll be discussing the experiment, but just to understand the possible cases, that if the object is between center of curvature and focus, then the image will be beyond center of curvature, it will be inverted and real. When the object is at the focus, then as I said, when the incident beams are parallel, they go and pass through the focus, and when the incident light is passing through the focus, then reflected one is parallel. So here you can see, if the object is at the focus, the light, we use this two ray diagrams, right? Whenever there are of course many lights passing, reflecting from this object and going towards the mirrors, but to avoid a lot of confusion here, we always consider two rays going from the object towards the reflecting surface. So one incident ray we considered going parallel from the object and another going through the focus. Here also one light is going parallel after reflecting from the object and it passing from the focus. Another part is going like this and coming here. So basically what happens is, the image we get is at infinity, or also you can say we get no image, because infinity itself is not any particular place. So we can say no image is formed, or the image is formed at infinity when the object is kept at the focus. When the object is brought even near, so we started with the case when it was between C and F. Then second case is when we brought it closer to the mirror, that is at the focus. Now when we are bringing it even more closer, that is between the focus and this pole of the mirror, when the object is kept at this distance in between this F and P, then the image is formed. Image is formed as actually a virtual image, which we know is always erect, and it's larger than the size of object also. And this we can see by looking into the mirror. We'll be able to see it, but we cannot obtain it on a screen. So these are the different positions of objects, which results in 3 different positions of images and their sizes. This is the case only for concave mirror, because for convex mirror we always get virtual and erect images. Their size may be different, but depending on the distance, but they always form virtual and erect images. So this was also the same information, that when they are at infinity, we find the image at focus and it's real inverted. When they are beyond radius of curvature, then it's formed between F and C. When it is at radius of curvature, the image is also at the same place when it is between C and F. So they started with more cases that when it's at infinity, it forms at focus. When it's at distance more than C, it comes between F and C. When it is at the center of curvature, image also forms at the center of curvature. And when between C and F, the image, as you can see, is beyond C. When they are at F, the image is at infinity or no image formed. And when the object is between F and P, that is focus and pole, the image is formed virtual and upright on the other side of the mirror, beyond mirror, which we cannot again obtain on any screen. So this is the cases, possible cases for concave mirrors. Okay, so it's basically what here I have just kept the characteristics of concave mirror, that by reflection of light, concave mirrors give real or inverted images. If the object is beyond the focus, these are the situations when it can give real and inverted images. Use of concave mirrors, depending on the distance, it could be used by dentists if they are, because they need to use it at closer distance so that they can get enlarged images. Whereas convex mirror, since it always gives virtual, erect and smaller image, we use in side view mirror in vehicles or shops and supermarkets, where we want to see in a small that mirror, we want to see a larger portion at the back. So there we use these. So they have their own uses. Now moving on to another characteristics of light, or another property that light shows, which is known as refraction. So refraction happens whenever there is change in the optical density of material. One we call density usually mass density, where we talk about the mass to volume ratio of a material. Here we are talking about, we will be speaking the term density, but here we mean optical density. Here we are talking about optical density. So air is the material for which we, refractive index, if you remember, we talk about different material have different refractive index. For air, refractive index we consider 1, and for optically denser medium it's more than 1, and if there is something even lighter than air, then the refractive index will be less than 1. So refraction happens, as I said, when there are two different material meet and they are sharing a boundary. Like as we can see in this diagram, we have air medium and glass medium, and there is an incident ray which is incident at this boundary, and now after incidence it's going inside this glass medium. So what happens, if it would have been reflecting, it would follow law of reflection, and angle of incidence will be equal to angle of reflection. But for that, the other material is opaque or the other side is polished so that it's completely reflecting. But if we don't have a completely reflecting surface, then some part of it could be refracting. Like the case here, glass is, we can see it's transparent, so the light, it's transparent means the light is passing through it. And when it's passing, so what's happening is, since it's going from a rarer medium to a denser medium, its angle, or it's basically what happens is its speed changes. The speed of this incident light is more in air medium, but its speed will decrease in glass medium because it's denser medium, and that will result in this angle of refraction that we call to change. So this change in the speed of incident light when it passes from one medium to another is what we call refraction, and it results in the change of this angle also. So we have two laws for laws of refraction of light as well. The first law says that the incident ray, refracted ray, and the normal to the interface of two media at the point of incidence all lie on the same plane. This is similar to the law of reflection, where we were saying that we were talking about a reflecting surface. Here we have this this we will say it's an interface, because on one side it's different material, on another side it's different material or different medium. So this boundary in scientific terms is called interface, and at this interface, if again we will consider an imaginary normal, then because we have to, as you know, angle of incidence is always measured from this normal, so that okay, so this normal we consider, and then our angle of incidence, this normal and this refracted ray all lie in the same plane. This is the first law. The second law is the ratio of sine of incidence angle to the sine of refractive angle is constant. This is known as Snell's law of refraction as well. That this incidence angle I, this refracted angle R, when we take sine of I and sine of R and take their ratio, this ratio comes out to be constant always. This law is also stated as this: if say refractive index of air, we say mu air, and the second medium refractive index is this, then we can also write it as mu air sine I is equal to refracting index of glass multiplied by sine of angle of refraction. So from here you can clearly see that sine I, ratio of sine I and sine R is ratio of refractive index of glass to refractive index of air. So this is the second law, which is also called Snell's law of refraction. Okay, based on this we will do I think one or two questions. So light traveling, the first question is, light traveling in air enters into an optical fiber of refractive index 1.44. So we have a light traveling in air and then it encounters another medium. So first it was traveling in air, then it encounters another medium which is an optical fiber. So optical fiber is given, its refractive index is 1.44, and we know for air refractive index is 1. That means this material of optical fiber is denser, optically denser than air. Okay. So the question is, in which direction does the light bend? Okay, let me draw it better. Here I have air, here I have this optical fiber, two different material medium. Now first let's draw a normal to this interface. This normal I am drawing perpendicular to the interface. If this is my angle of incidence, let's call it theta I. Okay. Now since the information is that refractive index of this optical fiber's refractive index is 1.44, that means is more than refractive index of air. So when, as I said, when the incident light goes from a rarer medium to a denser medium, its velocity decreases, and because of that the angle it makes with the normal or the refracted angle is always less than incidence angle. Refracted angle theta r will be less than incidence angle theta I if this medium in which it is going is denser. So in which direction does the light bend? the light bends towards the normal. If we'll reverse the case, that the material is going from this optical fiber, which is optically denser medium, okay, to air, we have reverted the case. Again, we'll consider a normal here, and this is the incident light, this is theta I. If light is going from denser medium to rarer, so velocity of light is less in this denser medium, but its velocity will increase in the rarer medium, and then it will go away from the normal. That means theta r will be larger than theta I. So these are the two possible situations whenever incident light passes through interface like this. So first question we answered, that because light is traveling from rarer medium to denser medium, its velocity will decrease and it will move towards the normal. Second part is, if the angle of incidence on one end of fiber is 22 degree, then what is the angle of refraction? Okay, so what it's saying is incidence on one end of fiber. So fiber material, if it starts beyond this, if it starts from here, maybe it's like this. Of course optical fibers are very thin. Here I'm just magnified this much so that we can understand. So the material starts from here, and it's saying the angle of incidence on one end of fiber is 22 degree. Consider the incidence angle is entering here at 22 degree. Then what is the angle of refraction? So from the Snell's law of refraction that we discussed, Snell's law of refraction, we know that mu air sine theta I will be equal to mu refractive index of this optical fiber multiplied by sine theta r. Okay, we have to find out what is the angle of refraction. We have to find out this value. So I'll take ratio of this, refractive index of air divided by refractive index of fiber multiplied by sine, and theta I is, we have been given 22 degrees, sine of 22 degrees. If we'll calculate the left side of this equation, I'll find out sine theta r. Then from that we'll be trying to find out theta r. So let's first do this. What is sine of 22 degree? I'm using calculator to calculate this. Sine of 22 degrees is 0.3746. Okay, this is 0.3746, and refractive index of air is 1. Refractive index of optical fiber given is 1.44. Let's calculate this also. 1 divided by 1.44 is 0.6944. So this will be 0.6944 multiplied by 0.3746. 0.3746, 0.26, 0.260. Now this that I have obtained is sine theta r, right? Now I need to find out theta r. For that I'll take sine inverse. Sine inverse of 0.260 will give theta r. Let's take sine inverse. Sine inverse of 0.260 is giving 15.07. So I can just approximate it to be 15 degree. So if the angle of incidence for this optical fiber system is 22 degree, then angle of refraction will be 15 degree, right, which is less than the angle of incidence because the optical fiber medium is denser. So what we had discussed, we are seeing that the law is giving us the result which supports our discussion. Okay, this was the first part, this was first question based on the law of refraction. Now next question is, light traveling through the If you guys have any question at any point of time, you can ask. Otherwise, we'll continue.
Yes, ma'am.
Yeah, okay, thank you. The
Ma'am, in the exam,
yes,
ma'am, I have one question.
yeah,
Ma'am, previous question.
yeah,
You are putting theta is equal to sine inverse of zero point 0.2 something, yes or no?
yes.
But in our examination, how we will put the sine inverse of that value in the calculator, ma'am?
You mean how you will be able to calculate or not?
Yes,
I
ma'am.
think
Yes, ma'am.
if these exams are, I think, computer based.
Hmm.
Have you given GATE exam or any online exam?
No, ma'am. No, ma'am.
Oh, I think so. What it happens, these exams, if you are enrolling for giving the exam for this course, you will see
Hmm.
that they are computer based. So, in the computer, you have a calculator there.
Okay, okay.
Or otherwise, these days in many
Hmm.
exams, they allow you the
Hmm.
scientific calculators.
Okay, ma'am. But in the hall ticket itself, they will put that, ma'am. We will get it the calculator, scientific calculator to the exam hall.
I think, yeah, because they don't expect you to remember this or anything. Because,
Yes, ma'am. That's
right?
why I'm asked.
Yeah,
Because sine
yeah,
inverse, we don't know how to calculate.
yeah, right.
Yes, okay. Thank you.
Yeah, okay. Clear?
Yes, ma'am.
Okay, thank you. Okay, so next part of this question is that light traveling through the optical fiber reaches the end of the optical fiber and exits into the air. So, first case we had seen that the incident light is entering the fiber, it was entering the optical fiber, there was refraction happening, and now after whatever is the amount of material, now this light will be exiting the optical fiber medium. Now this theta r on the other side of the material, it will be incident, this part will be theta I, which will be same, as you know, when we have two parallel lines and there is a line intersecting, there's this angle are same. So here, this for this light, the angle is theta r here, the same angle is becomes theta I. And now the question is, when it exits into the air medium again, after passing through this optical fiber medium, if the angle of incidence at the end of the tube is 30 degree, okay, so maybe here it's not the continuation of the previous, otherwise we would take the same angle. Here they are saying that we have to consider like this, that one side it's optical fiber medium, another side it's air medium, and they are saying if the angle of incidence at the tube when the light is exiting into the air, again we have to make the normal, when the light is exiting into the air, that time they are saying incidence angle is 30 degree. Then what would be the angle of refraction outside the fiber? What will be the angle? So one thing that we saw earlier, that when the light goes from air to a denser medium, its velocity decreases and it moves near to the normal. Here the case is opposite. It's going from optical fiber to a rarer medium. Thus its velocity will be more in the air and it will go away from the normal. It will go away from the normal. So now we need to find out. Again we'll use our Snell's law, which is mu. Okay. refractive index of this optical fiber sine theta I. Now this is theta I, this is the angle of incidence and this is the angle of refraction, is equal to refractive index of air and sine of theta r. So refractive index of optical fiber was 1.44 and refractive index of air is 1. Now sine of incidence angle, which is 30 degree, from this we will calculate refracted incidence angle, angle of refraction. So this will be sine 30, sine 30 is 0.5, 0.5 times 1.44 is 0.72. Now I'll take sine inverse on left side to get theta r. So sine inverse of 0.72 sine inverse of 0.7 sine inverse of 0.72 is 46.05. So if we have been given option, accordingly we can see maybe we can round it off to 46 degree as well. So this will be the angle of refraction. So these were the questions based on Snell's law or the laws of refraction. Now next move towards, so till now we were discussing law of reflection, law of refraction, and we also discussed the spherical mirrors, concave and convex mirrors. Now let's move on to the type of spherical lenses that we have. One is convex lens, this is convex lens, this is concave lens. Again, if we talk how we make it, as in previous case, again origin is same. We have a spherical material, we take its very small part, that will be like this. If I take another small part and join it here, then it makes convex lens. If I take these two parts and instead of joining it in this way, if I join it inverted opposite way, then the middle gets thick and basically it's this. So then it forms concave lens. According to their property, it's very interesting. All the characteristics that we see for concave mirror, like we saw, right, for concave mirror, based on the distance of object from the mirror, the image distance was also changing. In fact, the type of image was changing depending on the distance. It was changing from virtual image to real. All these properties of concave mirror is followed by convex lens, whereas all the properties of convex mirror is followed by concave lens. So this also is useful information. Now next, okay, I think or do I need to tell anything? Yeah, I think we can start first, or should I first I'll tell one more thing about this. Let me take one slide here. Like here I'm talking about image distance or object distance from the mirror or for the lens, from the lens. Now there is very important point we need to keep in mind, that depending on the, okay, let's First, there is something called, very important when we are dealing with these spherical mirrors or these lenses, sign convention is very important that we need to keep in mind. So if there is something called, we don't need to derive this, but there is a formula. So as I said, for a mirror or for a lens, we have this principal axis, we have center of curvature, we have focus, this length is called radius of curvature, this length is called focal length, this is radius of curvature, I mean till pole, this is called radius of curvature, this is called focal length. Okay, so there is a formula that is called, we can call mirror formula, that tells us the relation between object distance from the mirror is denoted by small u. This is the object distance. Object distance we take from the mirror, and when we say from the mirror means the pole of the mirror. So object distance we denote by small u. The image that is formed, that we denote by small v, and the focal length, which is the distance of focus from the pole of the mirror or lens, we denote it with small f. So for mirrors, for both concave mirror and convex mirror, the mirror formula is like this, that 1 over v plus 1 over u is equal to 1 over f. This is the mirror formula. This is how the image distance, object distance and the focal length are related. Whereas for the lens, both concave and convex lens, the formula is slightly different, which says that 1 over v minus 1 over u is equal to 1 over the focal length. So this is the lens formula or lens maker formula, it's called, and this is the mirror formula. So there is slight variation in both these formulas. Now here this v, u, f, we need to, depending on the type of mirror or depending on the type of lens that we are talking about, the sign of this image, the sign of the object distance, the sign of focal length is different. So basically what we do, I should have taken one more slide. We'll see for each case exactly what's happening, and we'll also do numerical problems where we'll repeat it many times, that how these sign convention are changing depending on the type of mirror or the type of lens that we are using. But basically it follows this rule that if this is the principal axis and say this is positive x-axis, okay, this is consider this is either this is the mirror or the lens. It can be concave or convex, like any of those four things could be kept here. If the incident light direction is towards right, okay, then distance, if we measure from this pole in this direction, if we are measuring the distance, this direction means in the direction of light. If this is the incident light and whatever object distance or image distance we are measuring in the same direction, then we consider that as positive. But if we are considering the distance opposite to the direction of light, then we consider that distance as negative. What do I mean by this is, if the incident light is in right direction, okay, and my object is kept here, I have to take the distance from pole. So from the pole I am checking the distance of this object, then the direction is towards left, which is opposite to the direction of incident light. So the object distance u I'll take as negative. Okay. And if the image is formed also on this side, if the image, say this is the image, if this is also formed on this side, which is opposite to the direction of incident light, then this image distance will also be negative. But if, say for some case, the image is virtual, then it will be formed on the other side. Okay. Then if I'll take the distance of the image from the pole, then I'll go towards right, which is same as the direction of incident light. In that case, I'll take the distance of image as positive. Okay. Similarly, if height of something, whatever the image is, if it is forming like above, or what we say is erect, then we take that height as positive. And if it is forming downwards, means it's inverted, then we take that value as negative. So these are the basic rules of this sign convention, and then we'll see because depending on the kind of mirror or the kind of lens that we are using, the image will be at different position. For some it will be on the same side, for some it will be on the other side, and thus the sign conventions will be changing. So let's first see what was the first experiment that was discussed. So this first experiment was to measure the focal length of a concave mirror. So okay, so here in this diagram we will try to understand. So concave mirror, again, it has outside of it has polished, so that inside curve is the reflecting part. So how we were doing it, again, for better explanation, I think you should go through the lectures, because the professor has demonstrated the experiment and tried to explain it very well. Here we will just focus on the working formula for how to find out the focal length of a concave mirror. So what he had done is let's keep our object between radius of curvature and the focus. If we are keeping it here, then we had discussed there are several cases, and one of the cases was when the object is kept between radius of curvature and focus, the image will be formed beyond the radius of curvature. The image will be formed here, and that image is real, it's inverted, and we can get it on a screen also. But the way it has to be done in a laboratory, this again is very nicely explained in the videos. But what we do is, after this object needle, we also keep there is a bench actually, on which we put our concave mirror, this object, which is actually a object needle, and then to find out the distance of this image, we keep one more needle that we call image needle, and we adjust the distance of this image needle till the inverted image, tip of this inverted image matches the tip of our image needle. When it matches, because here we have a scale, on this bench we have a scale, so we can find out the distance of this, we can find out the distance of this object needle from the pole. Similar way, we can find out if this matches with this, then I can say the distance of this image needle is same as the image. So yeah, so please refer to those videos to understand these experiments. But here, this was the basic theory behind this experiment. And the mirror formula, as I said, it's 1 over f is equal to 1 over v plus 1 over u. And let's see, as what happens is, for concave mirror, the focus is on this side. Why is the focus inside? Because when it was part of this sphere, even center of curvature will be inside. It's part of a very big sphere actually. So the center of curvature and the focus was inside this. So that's why for concave mirror the focus is on left side. Now the object, if you will see, the light from it is going towards right. This is the object. Light from this object is going in what to say, right direction, right side, whereas the distance of this object, if I measure, I will measure from this pole towards opposite direction. So object distance will be negative as per sign convention, and the image that is formed, that is also on the left side, so even image distance will be taken negative, and focal length also, if I measure it from the pole, even this is in opposite direction to the direction of incident light, so even focal length will be in negative. So yeah, this was the basic working principle of this experiment. And to find out this through this formula, we can always find out, we know where we kept our object, so we know object distance, and then by matching this tip we will be able to find out the image distance, and if you will put that in this formula, you can find out the focal length of this object straight away. There is one more way that was explained as graphical method. So what we have to do for it is, we'll keep on changing this object distance. Once we'll take measurement at this, then second time you can take measurement after changing it to some other distance. So as many times you can repeat this experiment. So for every u, let's call the first distance u1, another distance will be u2. Correspondingly, you will be getting v1 and v2. So what we are doing in this graphical method is, for different values of u, we will be getting different values of v. Now we need to plot it. While plotting it, we need to keep in mind that we just now discussed that we have to keep in mind the sign convention for concave mirror, and this sign convention for concave mirror tells us that object distance and image distance, in this case both are negative, and focal length is also negative. So u, we are taking this is plus positive x-axis, this is negative x-axis, this is positive y-axis, and this is negative y-axis. And when we are plotting, as I said, our image distance is negative, so we will plot on this side, and so object distance is negative and image distance is also negative, so we will be plotting on minus x-axis and minus y-axis. So when you will plot, when we will plot these data points, we will see a trend like this, and we know radius of curvature, I told, is 2 times the focal length, right? Radius of curvature was the distance of C from the pole, and I told the focus is exactly half of this distance. So if I want to find out, which is the aim of the experiment, is to find out the focal length. So if I want to find out the focal length, somehow if I get to know the radius of curvature, I can just take half of it and I'll be able to find out the focal length. So in this situation, what we are seeing is, this is u is the object distance, v is the image distance. As my object distance is decreasing, right, this is 0, as my object distance is decreasing, my image distance is increasing, which we had seen for concave mirror, that as we are at infinity or when we are coming closer from infinity, our image distance goes farther and farther. So that is the same trend we are seeing here. Now if I make an angle, if I draw a straight line cutting this graph exactly at 45 degree, what this tells us, this point, at this point this is 45 degree, this is 45 degree. That means the angle of incidence and angle of reflection both are equal. And if you remember, I had told that when light passes from, I had told very much in the beginning that if we have concave mirror or convex mirror and the light is passing through center of curvature, then it will go back in the same direction. So here also, if the angle of incidence is equal to angle of reflection at 45 degree, that means this represents our center of curvature, and half, so this data point will give us that. Correspondingly, u value will get, v value will get, and these values will be equal. This will represent radius of curvature, and half of it we will get as our focal length. This was one way. Another way is if we'll plot 1 over u and 1 over v. Again they will be in negative. Again we'll keep them in negative, and because it's inverted values, we'll get a straight line like this, and the straight line, we know the equation for straight line is y is equal to mx plus c. So from lens formula, if we'll rewrite this, this is the mirror formula. 1 is equal to f is equal to 1 over u plus 1 over v. If I'll rearrange this, 1 over v I'm keeping here, and other things I'm sending another side, then it will become minus 1 over u plus 1 over f. Now comparing this equation with equation of a line, we see this is y, this is x, right? This is x axis, 1 over v is y axis. That means this minus 1 is the slope of this line, which we can see it is the slope of the line, and 1 over f is the what do we call it, intercept. This is the intercept on the this is the y intercept. So this y intercept, that is this line where it is cutting the y axis at B point, this OB is the 1 over f that we want to find out. And then after finding this, I'll take 1 over OB, and that will give me the focal length. So straight away with this experiment, if I'll put it in this mirror formula, v and u, after considering the sign convention, I'll be able to find out the focal length. But these two were some graphical methods that we can use to find out the focal length value. Okay, so next question was, next experiment was determination of focal length of a convex mirror. So here the thing is, for convex mirror, as I said, for concave mirror we may get real image or virtual image depending on the distance of object. But for a convex mirror, the image formed is always virtual, erect, and it is on the other side. So if it is on the other side, like if I want to find out convex mirrors, this is my convex mirror, this is principal axis, I'm keeping some object here, this is a bench. I can, if I take this as 0 and I measure the distance of object from here, okay, I'm seeing the object, I can measure the object distance. But the image formed is virtual, that is the image formed is on the other side, so I cannot measure that. Thus, to find out the focal length of a convex mirror, we have to change the setup little bit. We have to introduce this convex lens so that we can get image back on this side. This whole experiment, it's very interesting, and again you should refer the lecture to understand it properly, because it's difficult to tell just by saying. Their professor has demonstrated it very properly and told why we have to introduce this, we have to take help of this convex lens to get that. Basic thing, as I told, because this is a convex mirror, image formed which will be virtual and erect on the other side. Thus, what I can see is the person who is performing this experiment is here. We can take the distance of this from here, but the image formed is virtual on the other side, cannot be measured. Thus, we are introducing this lens so that the final image we can get on this side again, so that I can measure the distance. So that was the twist in this particular experiment. And yeah, the later things are same. The same way we can use mirror formula to find out after we get object distance and image distance, we can use the mirror formula to find out the focal length for the same. Now, because we have time for numerical problems, so I don't think it's very much useful to discuss this, because you please refer the lecture video where the professor has demonstrated it very clearly. That will be better. And the third experiment was about determination of focal length of a convex lens. So here you will be using lens formula. So this is comparison with the focal length of a concave mirror. As I said, properties of concave mirror and convex lens are same. So for convex lens also, depending on the object distance, the image distance and type of images change, which is similar to the concave mirror. Only here the lens formula is what we use, and again with the same thing for concave mirror we were getting the image on the same side. Here for convex lens, the object will be on one side and we'll be able to see the image on other side. And okay, the sign convention here will be that, as you see, let me tell you, here my pen works, here the object, so the light, incident light is going in this direction, and my object is, if I take the object distance from the pole of the lens, then I'll have to measure it on opposite side. So this object distance will be taken as negative, whereas the image which is being formed on another side, if I want to calculate the distance of image from the pole, it will be going towards the right direction, which is the same direction as the incident light, right? So this image distance I will be taking positive. So object distance here for this convex lens, object distance will be negative, image distance will be positive. So this we have to keep in mind. And finally, if you will see this formula, one thing is negative, another thing is positive. So finally focal length will be positive for this convex lens. This is again the same thing. So this is for convex lens. As I said, it follows the same properties as shown by concave mirror. So for convex lens also, if some object is at infinity, the image will be formed at focus on the another side, because there is no reflection happening from here, right? Everything is passing through the lens, that is refracting, and the image will be formed on the other side, but the rules, it will remain same, that it will be formed at the focus. As I said, all the rays going parallel passes through focus. So if some object is there at infinity, it will go and form the image another side at the focus. Another case is if the object is not at infinity but just beyond the radius of the center of curvature, then it will form a real inverted image on another side, and the image distance will be between focus and center of curvature. When the object is kept at the center of curvature, then the image will also be formed at the center of curvature on the another side, and it will be a real inverted image. If we bring, so in all these cases you see we are bringing the object from infinity to near to the lens. This was at infinity, then we brought it closer. We kept it at center of curvature. Now we are bringing it even more closer. Between center of curvature and radius of curvature we have brought, and when this will be the case, the image will be formed. As we are bringing the object closer and closer, the image is going farther and farther. So now the image will be formed beyond radius of curvature on the other side, and it's still real and inverted. When we will take the object and keep it at the focus, then the image will be formed at infinity, or you can say no image will be formed. Okay, so after that, if you keep it even closer, that is between the focus and the pole, then it will form, it will appear as if it's making an image like this. This is the case of virtual image, and it will be erect. This happens when the object is kept between the focus and the pole of the lens. Then the rays will be going diverging actually, but it will appear that on the same side it's coming through this point A prime, and this will be a virtual image. We cannot get it on a screen, and that's why it's called virtual image. So this is the same properties as we had seen for the case of concave mirrors. Okay, now so these are the experiments that were discussed in this week's. Now we'll do questions based on this, because numericals are important for you to solve your assignment questions. So yeah, so first question is, an object is placed at a distance u from a concave mirror. So first we need to see, we have a concave mirror. First we should make this diagram so that we can put everything here, and the question becomes clear to us. So this is a concave mirror, and we'll make a principal axis here. This will be the pole. An object is placed at a distance u from a concave mirror of focal length f. Let's say this is the focus of this concave mirror, and at double distance we will be getting center of curvature of this concave mirror. Now the question is, under what conditions small and inverted image is formed? So for this, we know for concave mirror, until we come at the focus, we were getting inverted image which were real also. So this case is when the object is kept beyond radius of curvature, then we get the image which is formed between C and F, and the size is also small. So what happens is, if this is my object, okay, I consider again two rays to understand where the images will be formed. So if my object is here, or I can give it some other shape to avoid the confusion. This is my object. We consider one ray from it going parallel to the principal axis, and we know any ray going parallel to principal axis will pass from the focus. It will be a straight line, of course, it will pass through the focus. Another line we'll consider to be passing from the center of curvature. This diagram is not going good, otherwise I could show. If any light that goes from center of curvature, it will come back from center of curvature, right? I'm not able to make it, but any light passing through center of curvature will reflect back and come again through center of curvature. In this case, you see these two rays, it intersects at a point here, which is between center of curvature and focus of curvature. At this point this image is made and it's inverted and it's smaller than the object. So you can see it for different cases, but our question is asking under which condition we will get small and inverted image. So small and inverted image we will get when we will keep the object beyond C. That means beyond C means, yeah, because C or radius of curvature is 2f, so when we'll keep the object distance at more than 2f, we'll get the small and inverted image. So A is the correct answer. The second question is, an object is placed at a distance u from a concave mirror of focal length f. So we are again talking about concave mirror of focal length f. This is our principal axis. Under what condition the concave mirror forms erect and magnified image? So we know erect image is always virtual, and we had seen for lens also just now that this is focus, double of it is center of curvature, and when my object is between the focus and the pole of the mirror, in that case my image will be formed on the other side. My image will be formed on another side. So parallel ray going from it will be passing through the focus. This diagram is, let me use the eraser. It's a little difficult to make it using this pen here, but if I have a scale I would be able to make it better. That again we will consider two rays going from this object towards this parallel ray. When then it will be passing through the focus, and another ray will be, finally we'll see that we get an image here which will be erect, magnified and virtual in nature. So one ray parallel passes to the focus, another ray we can consider passing from the focus, another ray, okay sorry, I think the better thing to do is, I'm sorry, just it's difficult to draw things here. Let me make it again here. As in previous case, we have considered two rays, sorry, not this. Like in previous case, we had considered one ray going parallel, passing through the focus, another ray passing through the center of curvature. Let's do the same. That this is the principal axis, this is my mirror, this is focus, this is center of curvature, there is an object here. Whatever light is reflecting from this object and going towards the mirror, if it's going parallel to the mirror, it will reflect back and pass through the focus, and if ray from it is going through the center of curvature, then it will reflect from the same, and another side we'll see it to be coming from a point where our virtual image will be formed. So in this case, when our object is kept at a distance u, that distance is between focus and pole. In that situation, the image formed is erect, magnified and virtual. So this happens when image distance is less than focus. The zero distances means we are at the pole of the mirror. So when the object distance is between the pole of the mirror and the focus, that time we get virtual, magnified and erect image. So these were the two cases that we had discussed, many cases, and these were the two where, so you have to basically understand that how based on the object distance the image distance and image type changes, and that concept or that knowledge you have to use in these two. Now the further questions I think are all numerical questions. Let's do them now. We have less time also. So the question is, where an object to be placed in front of a concave mirror, again we are talking about a concave mirror of focal length f, so that n times magnified real image is formed. This question, okay, they should have clarified better, but the question is where an object should be placed in front of concave mirror. Where should we place the, there will be focus of course, there will be center of curvature on this principal axis. Now the question is where should we put the object in front of concave mirror so that the image formed is n times the size of object. So yeah, when we do sign convention, I forgot to tell you. So I was telling you when object is positive, negative, if it's magnified it's plus height and minus height. We have it here, okay, yeah, here we were discussing sign convention, right? Here we were discussing sign convention, and I told you that when the object is formed upright we take it as positive, and when it's downward we take it as negative. Also here we calculate magnification, which we take the ratio of image formed to the, I mean it's, we can call it h, this height of, or this object height if it is h, and image height if it is h prime, then magnification means image height to the object height, which comes out to be equal to the ratio of distance of image from the pole to the ratio of distance of object from the pole. Just keep in mind this information. For mirror and lens there is again some sign that we need to keep in mind, but basically this magnification, which is actually the height of image and height of objects ratio, also gives this distance of image from the pole and distance of object from the pole, their ratio also gives us the magnification. So now we'll be using this aspect or this property, so don't get confused that there is some mistake, because here h is height of the image but v is the distance of the image from the pole, but their ratio also gives us the magnification. So we'll use this property now. Yeah, so we were doing this question. So the question was where should I place the object so that the image is n times magnified than the object. So magnification formula I told, it's h prime divided by h, but we don't know the height of the image or the height of the object, but what we know is in terms of u and v we can tell. So as I told, it will be v over u, and for concave mirror we will see if it comes out to be positive or negative. But first thing we can, I think after making this diagram, first thing we should always write or keep in mind is what will be the sign convention for object distance, and sign convention of focal length, sign convention of the image formed when we are taking case of a concave mirror. So when we have a concave mirror like this, here the object distance is on this side and the ray will be in this direction, right? And object will be on the left side. So object distance will be negative. Image distance, we need image, real image. So all real images are formed on the same side. Only virtual image, if you remember, was forming on another side. Here we need real image. That means the image will be formed on left side. That means even that will be negative as per our sign convention. And focal length also for concave mirror is negative. So keeping these points in mind, now as I told, magnification is the ratio of image distance to object distance also. And so from this magnification we want n times. So magnification I want to be n times. They have not given any number, they have just given, say, the magnification has happened n times. That means the image distance is equal to nu, right? This relation we get from the magnification condition given. Now using the mirror formula. Now using the mirror formula tells us 1 over f is equal to 1 over u plus 1 over v. Now as per sign convention, this will become the focal length is negative, object distance is negative, image distance is also negative. So this will be our correct mirror formula. But here you see there is negative sign on both sides, so ultimately they'll become positive. If I'll take common negative 1 from this side and take it to another side, it will become positive. So this is my final formula. Now I'll insert the value. I want to find out u, object distance. I need to find out in terms of image distance and focal length. So I want to find out 1 over u, that will be 1 over f minus 1 over v. And from this condition I know v is n times u. V is n times u. Okay. Now the equation is this. If I'll rewrite and rearrange, then it will become 1 over f will be equal to 1 over u plus 1 over n times u. Okay. So now adding this, I'll get nu here and I'll get n plus 1. So when I want to find out f here, I'll take one more slide, it's okay. So we left it here. Now when I'll calculate f from here, or let me write this, 1 over f was n plus 1 over n times u. Basically I want to find out the value of u from this, right? So u will become n plus 1 divided by n, and f on this side will be here. So what are the options we have? Yeah, so our answer is matching with this. So this is the value of object distance, where we should keep our object so that we get the image n times magnified, and it will be real image also. So first, I think we should understand the steps. That first we should draw or keep in mind the type of lens or the type of mirror that we are talking about. After that, we should take care of the sign convention and then write our mirror formula or lens formula, then insert the value or the conditions that are given to find out the final parameter that has been asked. So let's do another question. And this question is, what will be the magnification? Again we are talking about magnification when the object is placed at a distance of 2f. Object distance is 2f from the pole of a convex mirror. again now here we are talking about a convex mirror, and we need to find out the magnification, which is again h prime h, or the image distance to the ratio of object distance. So we need to find out the magnification when the object is placed at a distance 2f. Object distance is 2f from the pole of the convex mirror, and the focal length of the convex mirror is given to be f. Now first we have drawn so that the picture is clear that we are talking about a convex mirror. Now what will be the sign convention for object and distance? So object we will be keeping here somewhere at 2f. For convex mirror, okay, for convex mirror our object will be here somewhere. That means it will be negative. So object distance will be negative. Then convex mirror always forms virtual image, that means on the another side. That means the image distance will be positive and the focal length will be negative, because from mirror formula also you know, and from here also you see, but from mirror formula also you know that 1 over f is equal to 1 over u plus 1 over v. So if one of this value is negative, another is positive, so focal length will ultimately have a negative sign. Okay, but wait, this could be different here for convex mirror. So okay, let's not say anything about this, but these two values we know will be positive. In fact, I think it should be found on this side. Let's see, this could be different depending on the magnitude of u and v. But from this graph we can see that f is on another side, so even this we can consider positive because it's on right side. Image is also on the right side, object is on the left side. So these will be the sign convention. Inserting them in this mirror formula, f is positive, u is negative, so I'll write it as minus u, v is positive. So this is my final formula for this situation. Now the object distance is 2f. No, so object or image? Okay, sorry, this was object distance. Yeah, this was object distance. 2f was object distance. Now when I put the value minus object distance is 2f, this will remain 1 by v. Now I need to find out what will be the magnification. To find out the magnification, I need image distance. From this, what I want to find out is 1 over v. So if I'll send this minus 1 over 2f to left side, it will be 1 over f plus 1 over 2f is equal to 1 over v, which will give, so it will be 2 plus 1 is equal to 1 over v, implies 1 over v is equal to 3 divided by 2f. It implies v is equal to, when I take reciprocal on both sides, I'll get v is equal to 2f by 3. So this is the image distance, and to get the magnification, I'll take the ratio of v by u. V is 2f by 3 and u is 2f. So its ratio will give me 1 by 3. That means the image is not magnifying, it's actually becoming smaller, and that also 1/3 of the object. So the correct answer is B, 1/3. Now the next question, the radius of curvature of a convex mirror. So we are talking about a convex mirror again. This is the principal axis. The radius of curvature is given for this convex mirror, and the radius of curvature is 100 centimeters. An object is placed in front of it. If the magnification of image is 1/4, magnification, which we know is the ratio of image distance to object distance. That magnification we have been given as 1 by 4. What is the image distance from the mirror? We need to find out. Okay, so first again, what will be the sign convention? U will be negative because the object will be kept somewhere here. V, it will form virtual image on this side somewhere, so V will be positive, and focal length also is on another side, so focal length is also positive. Okay, now the radius of curvature is given to be 100 centimeter. Radius of curvature is 2 times the focal length. That means f value we can find out, which is 50 centimeters, and from this relation, we know that V is U by 4. We have to find out V, and the relation between image distance and object distance is this. Now again, going to our mirror formula, which is 1 over f is equal to 1 over u plus 1 over v. But putting our sign convention into this, we'll get f is positive, u is negative, so minus u, v is positive, so it will be 1 over v. So this is my final formula that I can use for my convex mirror. Now substituting the values here, f is 50 centimeter, u is minus 4v, right? From this, u will be 4v. So when I'll put u is equal to 4v here, I'll get minus 1 over 4v plus 1 over v. So 1 over v minus 1 over 4v, 1 over v minus 1 over 4v means I'll get 4 minus 1, that is 3 divided by 4v. When I'll take reciprocal on both sides, I'll get 50 is equal to 4v by 3. This will be 3 times 50 divided by 4 is equal to v. When I'll solve this will be, let me use my calculator. This will be 50 times 3 divided by 4, which will be 37.5. I'm getting 37.5 centimeters value of image distance. So this is the correct option. Next question. When an object is placed at a distance of 10 centimeter from a concave mirror, as soon as we see that the type of mirror or lens has been told, let's draw it so that things will be clear in our mind. We'll follow the same step so that there won't be any chance of mistake. So this is the concave mirror, polished outside, reflecting inside, and two images. The question is, two images magnified. Wait a second. When an object is placed at a distance of 10 centimeter from a concave mirror, okay, so object distance is given to be 10 centimeters from the concave mirror, 2 times magnified virtual image is formed. So virtual image is formed. Object we are keeping somewhere here on the left. We are getting virtual image, means we are seeing it on another side. Okay, that means object distance is negative, image distance, which is virtual, for concave mirror, the virtual image forms somewhere here. So those things we need to keep in mind actually. There what is formed. For lens it's like this, for mirror it's on the same side, and I'm sorry. Wait, we are talking about a concave mirror. So yeah, the first, I'm sorry, let me, because of sign convention, sometimes we get confused. Because we have two types of mirror and two types of lenses, so while solving question we need to keep in mind which has what type of property. So yeah, for concave mirror we always get the image on the same side until we are talking about virtual image, which is virtual, which is on the another side, and we cannot get it on a screen. So that is on another side, and for this, since we measure it in this direction, it's negative. We measure this in right direction, it's positive, and the focal length of this is on this side again, so focal length is negative. So these are the sign convention. And what we got to know about images, the image is 2 times magnified, that means it's 2 times u, that means it's 20 centimeter. I mean, magnified it's telling, again I'm using the same logic. Magnification is the ratio of image distance to object distance, right? So magnification is 2 times, and h prime h, I mean height we don't know, but we know the image distance. We are talking about image distance and object distance, and magnification is also the ratio of this thing. So we are using that concept to find out. I'm using in this relation. This, if object distance is 10, magnification is double, that means image distance will be 20 centimeter. Now again our mirror formula, 1 over f is equal to 1 over u plus 1 over v. Now incorporating this sign convention here, it will become 1 over f, 1 over minus f, because it's negative. Then u is negative as well, v is positive. So this is my final mirror formula for concave mirror and for this particular condition actually. So this is my correct formula here. Now putting the values here, I need to find out, the question is, when an object is placed at a distance of 10 centimeter, 2 times magnified virtual image is formed. If the object is placed at 30 centimeter, where will the image be formed? Okay, so there are two cases here. For case 1, the object distance is at 10 centimeter and image is formed at 20 centimeter. We have to find out where will the image, that is we need to find out actually case 2, that where will be the image formed if the object is placed at 30 centimeter. For this information we need to know the focal length, and to find out the focal length we will use the first case, because here we know the image distance and the object distance. So we will find out focal length from here, and then we will use that focal length value for the second case to find out the image distance. Okay, so from this we will try to find out the focal length. So this will become 1 over f, this will become 1 over u, this will become minus 1 over v. I am taking the negative sign to right. Now 1 over u, this is, and v is 2 times u. V is 2 times u. So this will be 2 minus 1 over 2 times u. It will be 1 over 2u. 1 over 2. U is 10 centimeter. This will be 1 over 20 centimeter. That means focal length value I will get as 20 centimeter. And using this value of focal length, when I'll substitute it for the second case, for second case also we'll use the same sign convention, because no particular information is given. So I'll use the same. Again I need for this situation we had obtained, where is my n? Yeah, this after incorporating sign convention we had found this, right? Is it Amazon delivery? Is it Amazon delivery? Check. What's going on? So this is the focal length that we'll use for case 2. And so yeah, the equation that we got is, that we had obtained was 1 over minus f is equal to 1 over minus u plus 1 over v, right? So for second case we'll use this mirror formula, and the value here is, now we know the focal length, which is 1 over minus 20. Object distance is 30 centimeter. So we need to find out the image distance. So from this, when we try to calculate, I'll take it to another side. The value I'll get is, so it will be 1 over 30 minus 1 over 20. So it will become 60, it will be minus 3 plus 2. So 2 minus 3 is minus 1 over 60. It implies that V will be minus 60 centimeter. This tells us that the image will be formed at 60 centimeter. Image will be formed at the distance of 60 centimeter, but it will, since the value is coming to be negative, that means it will be formed on the same direction, same side. So it will be formed at 60 centimeter in front of the mirror, because then only the value will be in negative. Okay, so option A is correct. Yeah. So next question is, convex mirror uses an image at a distance of, so we are talking about a convex mirror. Convex mirror produces an image at a distance of, convex mirror always object is here and image is virtual on here. So image distance is negative, object distance is positive for a convex mirror. Okay, so what we are known as, image is formed at a distance of 8 centimeter. Radius of curvature of the mirror is 48 centimeter. We have to find out position of the object. Radius of curvature is 48 centimeter. That means focal length is half of this. That means 24 centimeter is the focal length. Now what will be the sign convention? Focus will be negative. Having focus for this is mirror, right? Convex mirror. The focus of, no, sorry. This is concave mirror. This is concave mirror. Convex mirror looks like this. So it's convex mirror, of course it always forms virtual image. And so yeah, so the focus here will be, this side. That means focus here will be positive. Sorry, there's different cases, as like we really need to keep in mind properly what's happening here. So U is negative, V is positive, focal length is positive. We know the value of V, we know the value of F. Now let's see what happens to our mirror formula. Initially we know 1 over f is 1 over u plus 1 over v. Now incorporating sign convention, it will become 1 over f is positive, u is negative, v is positive. So this is my final formula. Now putting the values, f is 24, so 1 over 24 minus u is, we need to find out u, minus 1 over u, v is 1 over 8. So from this we'll get 1 over 24 minus 1 over 8. So this will give 1 minus 3, which will be minus 2 divided by 24. This minus will be gone. So we'll get u is equal to 24 divided by 2. That will be 12 centimeter. And this distance is positive. That means it is kept the image to be placed in front of the mirror at a distance 12 centimeter on distance of object. Object is to be kept. Yes. So the answer is 12 centimeter plus 12 centimeter. Next question is, how much time we have left with this? Let me see how many questions we have. We have several questions. So this question is, an object of height 10 centimeter is held at a distance of 80 centimeter from a convex mirror. Again, so convex mirror means it's polished inside. Okay. Or I should draw for better clarity, because we have been using that particular direction, that will make it clear. Basically sign convention won't change, we have to just keep in mind the direction of light from the object, but because we are always drawing it this way, so again to keep it clear, this is our convex mirror, a principal axis, and for this the image object will be here, image will be formed another side, that means u will be negative, v will be positive, and focal length will be positive again, because focal length of this lens is here. Focal length will also be positive. So what will happen to mirror formula? 1 over f is equal to 1 over u plus 1 over v. This is its original form. After considering this sign convention, I'll get 1 over f is equal to minus 1 over u plus 1 over v. This will be my suitable mirror formula for this situation. Now, so I have been given object height is 10 centimeter, okay, and is held at distance of 80 centimeter from the mirror. That means object distance is 80 centimeter. Focal length we are given 48 centimeter. I need to find out size of image. Sorry, size of image. This is the size of object. Then what is the size of image? Again, you know magnification is the ratio of h prime, image height and object height. Also, image distance to object distance. Here we have been told size I need to find out, means magnification I need to find out. So This is my, I know F, I know U, I'll find out V first. Okay, so when I'll put my values in this mirror formula, I'll get 1 over 48. I need to find out V, right? So this will be 1 over U is equal to 1 over V. Just sending this minus 1 over U to left side, I'll get this. And V, U is actually 80 centimeter. When I'll solve this, I need to take LCM of 48 and 80, and when I'll do this, I'll be getting 1 over 48. From this, I'll get that image distance is, no, sorry. From this, I'll get image distances reciprocal of this. You can solve this, you'll get 1 over 30. So image distance will be 30 centimeters. Now we know V, we know U, so I can find out the magnification, right? In this, when I'll magnification, I want to find out V is 30, U was 80, and also this is equal to this ratio. H prime we need to find out. H I know, which is 10 centimeter. So equating these two, I'll get H prime is equal to 30 times 10 divided by 80. Okay, so this will be 30 by 8 centimeter. This will be 30 by 8 centimeter, which when I'll calculate, I'll get 30 divided by 8 is equal to 3.75. The answer is 3.75 centimeter. This is the correct answer. Now moving on to the next question. A convergent beam of light falls on a convex mirror. Again, this is the case of convex mirror. A convergent beam of light falls on a convex mirror. Convergent beam of light falls on convex mirror. The point of convergence being at a distance of 40 centimeter behind the mirror. After reflection by the mirror, the rays meet at a point 120 centimeter in front of the mirror. Calculate its radius of curvature. So first we need to understand this question by like after breaking it into small phrases. Incident light we are using, it's a convergent beam. Convergent beam means it's coming like this and converging at a point. Finally it's going to converge at a point. So this is a beam which is a converging beam. It falls, so it will converge because it's a convergent line, it will converge at a point. But before it converges, if you keep something here, and especially if you keep a convex mirror here, then all these converging lines, instead of being converged, they will scatter, right? I mean, they are coming like this, and if this mirror is not there, they will converge at some point. But since this mirror is there, instead of converging, they will scatter away from here, from this mirror. Okay, and the direction of scattering can be somewhere. What they have told is the point of convergence is at distance of 40 centimeter. This point of convergence is at distance of 40 centimeter behind this mirror. After reflection from this convex mirror, the rays, okay, so they are scattering in this direction. They are telling they are converging after reflection. They are meeting at a point 120 centimeter, means after the, again let me tell, so this is the convex mirror. We have been, what all things we have been told, that there was a converging beam coming which will converge at 40 centimeter behind this mirror. Okay, but since this mirror is there, they are reflecting back the converging beam, and the reflection is happening like this. If it would converge, it will converge here, at 40 centimeter distance, but since it's reflecting back, the information is they are reflecting and meeting at point 120 centimeter in front of the mirror. So the rays were coming like this, and instead of meeting here, they are going back after reflecting and meeting at point 120 centimeter in front of the mirror. This is the information given to us. Now for this thing, okay, now the question is calculate the radius of curvature. So for this situation, this is the final image. The image object here, you can consider object is, this is the object, and the image is forming at infinite at 120 centimeter here. So object will be positive, and which is 40 centimeter. Focal length is also here, so focal length is also positive for convex mirror. Now image is being formed on this side, so it will be negative, and also we have been told that image is forming as 120 centimeter distance. Okay, so when we will keep it in to find out the radius of curvature, which is 2 times focal length, we will first find out focal length. So our formula, which is 1 over f is equal to 1 over u plus 1 over v, after sign convention it will become 1 over f is equal to u is positive, v is negative. Okay, and when I'll substitute these values, I'll get u is 40 minus v is 120. So solving this, it will be 120. 3 minus 1, it will be 2 over 120, 1 over 60. That means focal length will be 60 centimeters. So we have to be careful. Focal length is 60, but we need to calculate radius of curvature, which is 2 times 60 centimeter. That means it's 120 centimeters. So 120 centimeters is the correct answer. I think we have one more last question. Let's finish this. A 3 times magnified real image of an object is formed by a concave mirror. So we are talking about now, we are talking about a concave mirror here. Okay, and 3 times magnified real image of an object is formed by a concave mirror. When the object is displaced 20 centimeter towards the mirror, a virtual image of the same magnification is produced. Find out the focal length of the mirror. Okay, so this question also has 2 cases. We have case 1, where a 3 times magnified real image of an object is formed. So for first case, the object is real, means the object is also on this side and the image is also on this side. In that case, the object distance will be negative and the image distance will also be negative, and the focal length will also be negative. This is for case 1, and the values we are given is magnification is 3 times. We know the ratio is image distance to object distance, and this is the magnification is 3 times, implies v is 3 times u. Okay, this is one case. From this we can try to find out our focal length. So what will happen to our mirror formula is, after considering sign convention, so because all 3 values are negative here, so we will again get this. Now just substituting this. Okay, but we just know this relation, we don't know u and we don't know f. Okay, but what relation we will get is 1 over f is 1 over u plus v is 1 over 3 times u. That means this is 3 plus 1, that is 4 by 3, 1 over f. From this relation we get f is equal to 3u by 4. Now for case 2, here the case 2 is when the object is displaced 20 centimeter towards the mirror. Now this object, whatever was the distance u, now I am changing the distance by minus 20. I am pushing it towards the mirror. So this new object distance is the old one minus 20. Okay. Virtual image of same magnification is produced. This time I am getting a virtual image. That means the image will be formed on this side somewhere. So by sign convention it will be negative. Object is anyway negative because it's on this side, and focal length is negative. So using this case, the mirror formula will be 1 over, like in this, if I substitute the sign convention, it will be minus f. Image is negative, sorry, object is negative, image is also, no wait, it's forming on another side, means this image is positive. So this will be like this. Now when we substitute the values, it will be 1 over f is equal to 1 over u minus 1 over v, and u is 1 over u minus 20, and v we don't even know. Wait, when the object is displaced 20 cm towards the mirror, a virtual image of same magnification. Okay, so for second case also the magnification is same. The magnification is same means the virtual distance is 3 times the image distance. So for case 2 also the magnification is 3. That means image distance is 3 times the object distance. So v is 3 times the object distance, and object distance has changed to this value. Again, a slide here. Okay, I have a slide already. So when we will solve this, so from first case we had got focal length is equal to 3u by 4, and sorry, from the second case I am getting 1 over f is equal to 1 over u minus 20, 1 over u minus 20, and minus 1 over 3u minus 60. Or let's let it be like this. From this it will be 3 times u minus 20. This will be 3 and this will be 1. So this will become 2 divided by 3 times u minus 20. This is 1 by f. This was for case 1. This is for case 2. So from this value, from this equation, the focal length will be 3 by 2 or 3 times u minus 20 divided by 2. When I equate these two equations, these two values of focal length, because in the two cases the distance of object is changing, but the mirror is same, so its focal length will remain same. So we can equate these two equations, and equating 1 and 2, we will get this. So this 3 will be cancelled. This will become 2. So u by 2 is equal to u minus 20. Then if I take 20, I'll bring it to the left side. U by 2, I'll take it to right side. Then it will be u minus u by 2. Actually u by 2. That means u is equal to 40 centimeters. u is 40 centimeters and we had to find out focal length of the mirror. So u I have found out to be 40 centimeter. Then if I'll substitute here, then f will be 3 times 40 divided by 4. This will be 30 centimeter. So focal length is 30 centimeter. So this was the last question for this session. So I think we have done more than enough questions to be able to understand how to approach these questions when we have these many different kind. Mostly we did all the mirror based questions. Next week maybe we'll be able to do all the lens based questions. So first thing is we have to keep in mind better to draw this mirror so that we can think accordingly where the object is, where the image will be formed for this mirror, and we should write down the sign conventions and then change the mirror formula accordingly, and the rest can be done easily. So these were the questions and these were the topics related to this week's session. Okay, and if there is no question, I think we can end this. Okay, I'll stop this. If you guys don't have question, then I'll stop the recording.